গো লাইভ করেছি, দাঁড়া গো লাইভ করেছি এখানে আমি, এবার দেখ
গো লাইভ হয়েছে।
গো লাইভ এখানে করলাম, এখানে এসে করতে হবে এই তো
শো করাচ্ছে তো,
সেটা দেখ, সেটা যদি লাইভ হয়
এখানে এখানে লাইভ শো করাচ্ছে তো, এই তো ঠিক আছে।
দেখে নিই
লাইভ দেখাচ্ছে,
দেখাচ্ছি তো, অফ করে দিই,
কেন অফ করো না, লাইভ থাক,
তখন ইয়ে করে দিব, পাবলিক করে দেবো,
তখন পাবলিক করবে, লাইভ থাক, আর লাইভ অফ করো না। এবার তুমি স্ক্রিনটা ইয়ে করো,
রেকর্ডিং তো করা দরকার নেই এখন আর।
রেকর্ডিং করার প্রয়োজন নেই। এটাকে শিফট ধরে টেনে নিচে সমান করে দাও। এটা করছো তুমি তো গুগল মিটে যাবো, এটা করে রাখছি না, গুগল মিট খুলে দাও এবারে,
গুগল মিটে দেখাবে কি,
তারপরে স্ক্রিনটা গুগল মিট শেয়ার করে দেবো, কথা বলি 34, তুমি ঢুকে যাও, তুমি ঢুকে যাও, তুমি ঢুকবে না বলছিলেন না, তুমি ঢুকে যাও।
ক্যালেন্ডারে কি করে দিই
কেন তুমি ডিরেক্ট গুগল মিট, হ্যাঁ ক্যালেন্ডার, হ্যাঁ তোমার আমাদের সেই লিঙ্কটাতে ডিরেক্ট খুলতে হবে, ঢুকে যাও, যেটা আগের থেকে ঢুকতে চাও ঢুকে যাবে। না স্লো আছে সেটা, মাথা তো গরম হয়ে, স্লো হলে তো মাথা গরম হয়ে যাবে।
এখানে মিটে গেলে
কেন আমার ডেট যে টাইমটা ছিল
সেটা সেখানে কি, সেটা এখানে মিটে গেলে দেখাচ্ছে, দেখানো উচিত আর কি,
শুধু সেখানে দেখা, তখন টাইম হয়ে গেলে দেখা, আমরা টাইমটা তো সেটা দেখেছি,
টাইমটা চেঞ্জ করবো, ওখানে এডিট করে দিব, হ্যাঁ বুঝতে পারছি, বুঝেছি, দেখাচ্ছে কিন্তু এখানে,
এখন দেখাবে না, এখানে
দেখানো তো উচিত, 8 ঘন্টা আগে রিমাইন্ডার দেওয়া আছে,
হয়ে গেছে 34, হ্যাঁ 34।
এই যে চলে এসে, এখানে চলে এসছে, শুরু করে দিই,
এখানে তো স্টার্ট করতে পারবে, সেখানে টাইম চেঞ্জ করো, এখানে স্টার্ট হবে,
হ্যাঁ স্টার্ট হয়ে যাবে, হয়ে যাবে,
হ্যাঁ স্টার্ট হয়েছে। তুমি ক্যামেরা, তোমার ক্যামেরা অফ করে দাও, মাইকের ক্যামেরা অফ করে দাও। হ্যালো হ্যালো হ্যালো, মাইক্রোফোন ইয়ে হ্যালো, ক্যামেরা স্টার্টিং, তোমাকে তো প্রেজেন্ট করতে হবে, না প্রেজেন্ট,
প্রেজেন্ট তো করা যাবে তখন,
আচ্ছা তো হ্যাঁ তখন স্ক্রিন শেয়ার হয়ে যাবে।
প্রেজেন্ট আমি করবো না, প্রেজেন্ট তো ইয়ে করবো,
আগে আসো এখানে, তারপরে বাপরে ব্যাস, এবার ওবিএসএ অলরেডি পাঠিয়ে দিয়েছে,
স্নেহদীপ সাহু, এখন থেকে নিবো না কিন্তু,
এবার তুমি ডিরেক্ট ওবিএসএ যাও, সোর্স দিয়ে অ্যাড সোর্স করে ইয়ে এটা ডাবল ক্লিক করো, এখানে চেঞ্জ হয়ে যাবে, এটা ইয়ে করে রাখো। ক্যামেরা অন আছে, ওকে এটা অলরেডি ঠিক আছে, ওকে করো।
ঠিক আছে, ঠিক আছে,
তোমার এখানে মাইক অফ করো,
মাইক অফ করে দিই,
ওবিএসএ ঢোকো, ওখানে তুমি তোমার মাইক্রোফোনটা অফ করে দাও, মাইক্রোফোন এখানে এখানে মিউট করে দাও।
did it really happen that Newton just looked at the apple and the whole idea of gravity came to his head and he got it all done in a flash of brilliance? By all accounts, no, it didn't happen that way. So what happened was that actually Newton had to work very hard, and we shall later talk about this a little more. He worked very hard to lay the groundwork for the law of universal gravitation, and he built upon previous work by others. It was not just Newton's work, he built upon previous work by others. But of course, he had a great realization about gravity, which perhaps nobody else had at that time. And we shall see what this great realization was. And he also worked with a lot of astronomical data, which he procured from various sources. He invented new mathematics to derive not only theoretical results, but to also analyze this data. And he worked almost exclusively on dynamics for 2 years in a later phase from 1684 to 1686. As I told you earlier, that he did not work much on dynamics between 1667 and 1684, but in the following 2 years, he really worked very hard on dynamics, and he put together all his thoughts and his work of the previous 20 years to finally write his magnum opus, that is the Principia. So it certainly took much more than an apple. Okay. So where does the apple come in? We shall see. But it all started in the sky. It all started with astronomy, because Kepler's laws of planetary motion were published between 1609 and 1619, and we are also laws. So the first law says that the planets go around the sun in ellipses with sun at one of the foci. They sweep out equal areas in equal time, and also that their time period, the square of their time period, is proportional to the cube of the centimeter axis of this ellipse. So these laws were, of course, based on Tycho Brahe's precise observations. Tycho Brahe was a Danish astronomer who made extremely precise observations of various objects, including the planets. And then they were worked upon, they were analyzed, that enormous data was analyzed by Johannes Kepler, who was German, but who worked for a long time with Tycho Brahe. And that came out as Kepler's laws. So Kepler's laws came before the theory of gravitation. This is, of course, something that is mentioned and that is known, but perhaps not always realized by students. So no theoretical basis yet existed for the elliptic shape of the orbits and on the other features of planetary motion, namely the other two laws of Kepler. Okay, so this was the status in the middle of the 17th century. So how did Newton figure all this out? So somebody asked him once that how did he arrive at the law of gravity, and Newton's answer was that by thinking about it continually, any pensant sans effet in French. But certainly, I mean, this may well have been true, but of course, many people think about many things all the time and still they make no headway. So it took a Newton to make it. But perhaps some clue can be obtained from this alternative picture of Newton sitting in his garden with the apple falling. And this is actually quite illuminating, because it shows, you can see in this picture that Newton is looking at the moon in the sky. And it was this that actually drove Newton finally to the law of gravity, when he considered the falling of the apple and the motion of the moon in a unified framework, as we shall see. And that's how it all happened. So Newton noticed the following things about the falling apple. So first of all, he noticed that the apple falls vertically to the ground. Okay? Now this may seem trivial, but what Newton realized is that even though there is earth all around below the apple, the net force on the apple is such that it is attracted directly towards the center of the earth. Now, even before Newton, or maybe parallelly with Newton, people had figured out that the apple falls to the ground because perhaps the earth is pulling it by some invisible force. Okay? So that is not something that was only Newton's idea, as is sometimes believed. But Newton laid great importance to the fact that the apple falls vertically, that is, it is going directly towards the center of the earth. Okay? And this puzzled him for a long time, and as we shall see that this has some implications. So he surmised that the whole mass, surmise means he guessed basically, or he did not have rigorous proof yet, that the whole mass of the Earth must appear to be a point mass at its center to an object like the apple, which is external to the Earth. Okay. Now this is not a trivial result actually, and although Newton drew the correct conclusion in the plague years itself, he did not immediately have a rigorous proof for it. Okay, and this is one of the reasons which actually stalled publication of his results by himself for 20 years. Much later, in 1684 or soon after, he proved it rigorously using geometry, and this proof is included in Principia. Okay. Newton also, as I said, wondered about the motion of the moon. And he realized the following thing about the moon, that as the moon goes around the Earth, in effect, the moon is continuously falling towards the Earth. Okay. Now, it does not fall into the Earth because its velocity is so great, so it keeps missing the Earth continuously and keeps going around it. Okay. But this idea that the moon, as for that matter, any planet around the sun, for example, as the moon goes around the Earth, it is not, its motion can be thought of as a fall towards the center of the Earth. So now, of course, we know all this to be true, but at that time, this was quite a novel idea, and nobody had really thought of it that way. Okay. So at every instant, the acceleration is directed towards the center of the Earth. Okay. Now, if you take a circular orbit and you take the velocity v of an object, which is of course tangential to the circle at every point, then you can show that the acceleration, which is the rate of change of the velocity, that vector is directed towards the center of the circle. So, and Newton proved it actually. So, but the question of how to calculate this acceleration. What is this? How does one calculate this acceleration? So this was an important step again. Okay. And Newton derived the formula for the centripetal acceleration, that is the acceleration towards the center of a body in a circular orbit, by calculating the change in velocity at every point. And his proof was actually a geometric proof, which used arguments similar to those in vector addition. Okay. And he found this very familiar formula that we all know now from school physics, that this acceleration is v squared by r, where v is the velocity, the linear velocity, and r is the radius of the circle. Okay. So Newton proved it at that time, during those plague years. Now, the famous Dutch physicist Christian Huygens, who is of course known for the Huygens principle in optics, we are all familiar with it. Now, Huygens had also derived the same formula, but by a slightly different method. And he had even published it in 1659. Okay. And again, as a general result in 1673. It's not entirely clear if Newton knew of this right from 1659, because in those days, of course, I mean, the communication was sparse. Newton was somewhat isolated in England, in Cambridge, or before that in Woodstock. And whereas the communication between the European scientists on the continent was more. So many European scientists knew about Huygens' result of the centripetal acceleration, but it's not clear if Newton knew it. Anyhow, he appears to have derived it using an independent method, a different method, but he did not publish anything. So Newton did not publish this result, although he seems to have derived it right in the plague years, that is around 1665. Now, this formula was necessary to calculate the acceleration of the moon. So the picture is like this, that the apple falls towards the Earth with an acceleration g, and the moon also falls towards the Earth with an acceleration which is v squared by r. Okay. Now, this acceleration g, the gravitational the acceleration due to gravity, this was of course well known, but nobody knew how to calculate this v squared by r, or nobody at all thought of calculating this for the moon in particular. Now, Newton's great idea was to think that do they fall under the same kind of force? Does the force, so this was Newton's original real great contribution, that he thought of the motion of the apple and the motion of the moon to be of the same origin. Okay. Nobody had really thought of it that way. People were concerned about planetary motion, yes. People were concerned about why or how the Earth falls to the ground, but nobody had really made this connection which Newton was able to make. So Newton thought that the same force which pulls the apple to the ground from the tree, maybe that force is not limited to just the immediate vicinity of the ground, that is the tree or some other hill or something, but it goes all the way up to the moon or maybe even beyond. Okay, so the question was, what is this r, that is the distance from the center, to be used in each case? Okay. So Newton decided to test it, which is called the famous moon test of Newton. So now the acceleration of the apple towards the center of the Earth, that was of course well known. This was at that time, of course, known in feet per second square, and today we know it as 9.81 meter per second square. This was perhaps already determined by Galileo, and anyway, this could have been determined using simple experiments. Now, the acceleration of the moon towards the center of the Earth is the centripetal acceleration, as we have said, that is Vm square by Rm, where Vm is the orbital velocity and Rm is the distance of the moon from the center of the Earth. Okay. Now, this is what Newton used, but he did not have a rigorous proof of why this is justified. Okay. But anyhow, he did this, and assuming a nearly circular orbit of the moon around the Earth, one can now say that Vm is equal to 2 pi Rm, that is the circumference, divided by the time of the revolution of the moon around the Earth, that is t. So if you substitute this, then you get Am equal to Vm square by Rm equal to 4 pi r square Rm by t square. Now, in this, the time period of the moon, the orbital period, was known to be 27.3 days. This is, of course, we know that the full moon or the new moon occurs every 29.5 days. But actually, if you correct for the motion of the Earth around the sun, then the moon actually completes a 360-degree revolution around the Earth in 27.3 days. Okay. Now, so that the t was known. Now the Greeks, namely Aristarchus initially, and then Hipparchus and Ptolemy afterwards, also from Egypt, they already estimated the distance to the moon to be around 60 times the radius of the Earth. Okay, so this was known to Newton, that the distance to the moon was around 60 Earth's radius. So now he calculated first the ratio of these accelerations of the apple, the AA, divided by the AM, the acceleration of the moon. So this is, of course, by the above formula is gt squared by 4 pi square Rm. He plugged in the value of Rm to be 60 Re, and the T, which was known, the G was known, and he got a result. Actually, he got something around close to 4,000 because he used slightly different values. But if you get it, put these values, you will get a value very close to 3,600. Okay. Now, the apple is at a distance Ra equal to Re from the center of the Earth, because the apple is sitting very close to the surface of the Earth. So that is the Re is the radius of the Earth, while the moon is at a distance of 60 Re. Therefore, Rm by Ra, this ratio turns out to be 60. Okay. The crucial point here is that the distances that matter are the distances of the objects from the center of the Earth, not from the surface or any other distance. Okay. Now, today it might seem very trivial, but at that point it was not clear why the center of the Earth has to be taken. Even to Newton it was not clear, and he had doubts about this, as we learned from his biography. So, but anyhow, Newton noticed that this ratio of these accelerations are pretty nearly same. These are his words. They answer pretty nearly the same, and the ratio of the accelerations is pretty nearly in the inverse ratio of the square of the distances. So the AA by AM is 3,600, which is equal to 60 square, which is the inverse ratio of the distances of the apple and the moon. So the moon test was therefore successful. So Newton could therefore immediately conclude that at least it's plausible that the same kind of force is responsible for both the apple and the moon's motion. Now, common experience, of course, suggested that the force is proportional to the acceleration. So Newton realized that if the force is inversely proportional to the square of the distance, then the motion of the apple and the moon can be explained by a single law. Okay. Now, this was the momentous realization of Newton. And this seems to have happened right in the plague years of 1665 to 1667, when he was working from home, as we are all now familiar with the term WFH. So Newton was also WFH at that time. So later, by using the third law of motion, which he actually enunciated later, he could obtain the dependence on the product of the gravitating masses and could arrive at the final law for gravitation. But this inverse square nature of the law was already done in those plague years. And then 20 years of silence. He did not publish it. Nobody knew about this result apart from Newton himself. Okay, he did not publish any of this. And later on, he says he has told people, and this is there in his biography, is that all this was done in those plague years. And he says that in those days, I was in the prime of my age for invention and minded mathematics and philosophy more than at any time since. Philosophy, of course, at that time, science was called philosophy. And so Newton was also later on, when he reminisced, he realized that he had done a lot of work in that. He not only worked on this, actually, during the plague years, he also already started his great work in optics. Anyhow, he did all this, but he did not publish it. Why? So it seems that the major stumbling block was perhaps he did not yet have a rigorous proof to show that the entire mass of a spherical body can be taken to be at its center and considering its interaction with an external body. Okay, because he thought that, okay, if really the Earth or every particle in the Earth is pulling on the apple, so they're pulling in all different directions, right? There's a vast land of Earth beneath the apple, so they're all pulling. There's also a lot of mass inside the Earth all the way down, and they're all pulling the apple. Why is it that the apple goes directly towards the center? And he did not have a rigorous proof for it. This seems to be one of the major problems why he did not want to publish it. Also, it has to be kept in mind that at that time, he had not at all formulated the three laws of mechanics that we are so familiar with today. Okay, so which would definitively provide the connection between acceleration and force. From common experience, it was clear that, okay, to produce the same acceleration in a greater mass, you need a greater force. But how that is exactly related, nobody had enunciated, neither had Newton at that time. Okay. And of course, he started working on other things, on optics, and various other experiments. But as this has been beautifully written by Richard Westphal, who has written the most authentic biography of Isaac Newton, called Never at Rest. So Westphal says that some idea floated at the border of his consciousness, not yet fully formulated, not perfectly focused, but solid enough not to disappear. He was a young man. He had time to think on it as matters of great moment required. So this is most likely what happened. He had this great idea in 1665, and remember, he was only 23 years of age at that time, and this great idea, he had it in his mind. He had not yet fully formulated it. He had not yet focused it fully. Okay, he did not have all the components in it. Okay, and then he started working on some other things. But as he says later, that he thought about gravity all the time. Okay, but he never had the real impetus to work on it very hard and finish it, which he did later. And we shall see why and how that came about. So, of course, Newton was not the only ones thinking. There were great scientists in Europe and maybe in other parts of the world also, but we don't know much about other parts of the world. But certainly in Europe, there were scientists who were thinking about it. And by mid-1670s, the European scientists began to conjecture that the force that makes the planets move around the sun may be an inverse square force. I want us to keep in mind that Kepler's laws were already there since 1619 or so, okay? And there was no answer to why the planets should move in elliptical orbits around the sun. So obviously people were thinking about it. The idea of force was already there, even before this, even from Galileo's time, or perhaps even before that. But nobody knew what kind of force it was. But so people are trying to figure out. But also, Huygens result of the centripetal acceleration of v square by r was there. So this was used by the scientists. So, but they could do it for circular orbit. Okay, people also knew that the planets move in nearly circular orbits. At least most of the planets did, including the Earth. So if you assume a circular orbit of radius r and period t, the velocity v is simply v equal to 2 pi r by t. Now, already Kepler's third law was there, which said that t square proportional to r cube. Of course, for a circular orbit, the semi-major axis a equal to r, the radius of the circle. Now, if you plug this in there, then now you use Huygens result, that is the acceleration is v square by r. You put for v 2 pi r by t, and you get that the acceleration is proportional to 1 by r square. So that it could be an inverse square force was already realized by several scientists in Europe, okay, including in England also. So although the inverse square force was a correct guess, but nobody had done the required mathematics to prove it conclusively. One thing was that the connection between force and acceleration was not yet made. Okay, they could show that the acceleration is proportional to the inverse square of the distance, but what was the connection between force and acceleration was not known yet. Secondly, this conjecture held only for circular orbits. Now, Kepler's elliptical orbits posed a huge mathematical challenge. Nobody could really solve and show that for ellipse also this kind of law would work. Okay, and it was only a law for the planets. It was not generalized beyond that. This is one of the most crucial points. Nobody other than Newton had really connected it and made it a universal law as Newton did. Okay. They were trying to explain the motion of the planets. So around 1684, there were three famous scientists in London. They met on various occasions. The first was Edmund Halley, who is famous for his comet, Halley's comet as we know it. Then there was Christopher Wren, who was in this picture you can see, who was the chief architect of the St. Peter's Cathedral in London, which is in this picture. And then there was Robert Hooke, who is also a familiar name from Hooke's law of elasticity, and who was actually a bitter rival of Newton all through his life. And they discussed this inverse square law for the planets. Now, at this time, all these people were based in London, and Newton was in Cambridge. This was around 1684. So the plague was gone. Newton had returned to Cambridge, and he was a professor there. So they discussed this, and they were stuck on this problem. So the story goes that they met in a London inn. So an inn is like a cafe of today. Okay, in London you can still find inns, so where people go to have a nice time, to have drinks and all. So the story goes that Wren put a prize in this meeting, and he said that he will gift a book worth 40 shillings, which was reasonably good amount at that time, but certainly not commensurate with the magnitude of the problem that was at hand. But anyhow, Wren promised a gift of a book of 40 shillings to anybody who would come out with the correct explanation for Kepler's laws of planetary motion within 2 months. Okay? And who claimed that he had the proof, that he could show that it was inverse square. But he said that he won't reveal it to anybody till others have tried and really realized how hard it is, so that he is properly appreciated. Anyhow, nobody knows whether Hooke did it. There's no record of Hooke having proved this, and he never provided it to Wren. And Wren also was perhaps was somewhat skeptical of Hooke's claim, okay, and so was Halley. Now, at this point enters Isaac Newton. So in August 1684, Halley traveled to Cambridge, where he met Newton. And during the course of conversation, he asked Newton the following question, that what would be the orbit of an object under an inverse square force? This was the question that Halley asked Newton. And Newton immediately answered that it would be an ellipse. Okay? And Halley was extremely surprised. And he asked, how? How do you know this? And Newton said, because I have proved it 20 years ago, that is during the plague years. So Halley said, okay, show me the proof. And Newton looked in his papers, and he could not immediately find the papers to show it to Halley. Now, all this is, of course, as we learn from Newton's biography, and there are conflicting versions of whether Newton really could not find the papers or whether he was very careful. Anyhow, he did not immediately give it to Halley, but he promised that he will send it to Halley, and he did so a few months later in November 1684. What he sent was not only this proof, it was actually a 9-page paper, which was called De Motu Corporum in Jarum, which translates, so this was, of course, all in those days people wrote in Latin. So the translated title is On the Motion of Bodies in an Orbit. Okay? And in this, Newton went further than what Halley had demanded. He even proved the converse, that is, he showed that an elliptical orbit must necessarily imply that the force is inverse square. Okay, so he proved the problem both ways. He showed that inverse square law gives elliptical orbits. He also showed that if the orbit is elliptical, then the force must be inverse square. He also derived Kepler's second and third laws. Okay, and he just sent it to Halley in November 1684. On receiving this, Halley immediately realized that this was an enormous step forward in physics. Okay, he realized its importance immediately. He made a second visit to Cambridge, and he asked Newton to publish this work. And Newton said that he had no money to publish it, because in those days, the publications typically happened in the form of books. So you have to find a publisher who would publish and print your book. And Newton said that I have no money to do that. And Halley tried to get the funding through the Royal Society of London to fund Newton's book. But even the Royal Society at that point was short of money for some reason, and they did not agree to publish it. Finally, Halley agreed to pay for it himself out of his personal money, and he did so. And he asked Newton to work on it. And Newton started working on it. He worked extremely hard and continuously on the topic for the next 2 years. And how hard he worked can be, some account of that is actually obtained from the narration of people who were around him at that time. One of them was his nephew, Humphrey Newton, and he writes that he actually often forgot to take meals. He did not eat always. He ate very little sometimes. He would walk out onto the street and immediately come running back and start writing the manuscript even while standing, because he realized that some great idea had come to him. And he was completely seized of this matter for the next 2 years. Okay, so it was a lot of hard work. I earlier said that this discovery was not just a flash of brilliance. There was a lot of hard work, okay, like most of scientific discoveries. So, and finally, at the end of it, Principia was published on 5th July 1687. After I agreed to give this talk, I realized that today is 4th July, so we are almost at the anniversary of Principia. And this was published in 1687 with Halley's money. And in this work, as a precursor to his theory of gravitation, Newton developed the laws of motion in Principia, and he did much more. He gave a rigorous proof of that problem that he had earlier, that the mass of a spherical body can be considered to be concentrated at its center. He also showed many other results related to mechanics, for which he derived mathematics. He derived various numerical methods and a lot of geometrical proofs. And all of that he put together in Principia. Basically, his work for more than 20 years he put into this. And that changed the course of science, as we know. Science would never be the same again. Once Newton's laws were there, once Newton's law of universal gravitation was there, this was a turning point, not only in the history of science, but in the history of mankind, one can say. Because everything that has happened after that was in some way or the other linked to Newton's laws. So this was truly a turning point. So by announcing this universal law of gravitation in Principia, so the word universal I've highlighted because that is one of the most important features of this law, that it is universal. He connected the terrestrial phenomena of the apple falling from the tree to the celestial motion of the moon and the planets in the sky. Nobody else had this idea. And that is where the greatness of Newton lies. Okay. So this was the first major unification in science. Today we talk about unification of various forces, and some unifications have been done. People are all the time trying for more unifications of the fundamental forces. But this was, in a sense, the first major unification of science, that two very different phenomena could be explained by the same law. Okay. So this was the major point in the history of science, I would say. Okay. So at this point, I would switch tracks a bit, and I would now. So this was the story of the discoveries, if we can say so, of the universal law of gravitation. And as perhaps I've been able to convince you, that it is not just a flash of brilliance of somebody just seeing an apple fall from the sky, or even somebody just looking at the moon or wondering about the motion of the planets. It takes some excellent insight. It takes some bold guess, as Newton himself has said, and also plenty of hard work. Okay. And that is what it is. Okay. Now, in the remaining time, I think I have maybe about 15 minutes or so. So what I'd like to do is to discuss a few of the subtleties of the Newton's laws of motion, the three laws of motion that we talk about. And this is mainly meant for the students of among the audience. The experts, of course, all know it. The experts know even the previous story that I told, as I said, it is all there. None of this is new. But I'd like to now switch tracks a bit. So how did Newton get to his laws of motion, which were also there in Principia? Okay, because he had to build those laws in order to arrive at his law of gravitation. It was all part of the same endeavor. So first of all, we talk of Aristotle. Aristotle, as you know, is a famous Greek philosopher who lived around 350 BC. And Aristotle was among the first who thought about motion of bodies in a deep, rational way, somewhat rational way. Of course, there were others also across the globe. Perhaps even in India, we had Rishi Kanad and others who were thinking about this in a rational way, not in a matter of faith or something, but in a logical way. But of course, most of the further development happened from the Greek line of thought, and Newton and Galileo before him were, of course, influenced by Aristotle and how they developed his ideas further. Okay, and how some of his ideas were contravened by or countered by Galileo and Newton. So what was Aristotle's theory? So Aristotle's theory was that an external force is required to keep a body in motion. Okay. Now this is a conclusion which arises from common experience, right? We see that, okay, there's let's say a box on the floor, and if the box has to be moved, I have to push it, right? Or if there is something, if there is some water at the bottom of the well, in order to bring it upwards, in order to make the water move, I have to pull it up, right? So to produce motion, I need some force. This, of course, appears to be so. Okay, but the fallacy in this, of course, is that it does not take into account all forces at work, right? We all know this, that we need to push the box continuously to move it because friction is opposing it. So the moment we stop pushing it, it stops because of friction. If there's no friction, then the box would keep moving after we have given it some initial velocity, but that does not happen. So, and this, of course, Aristotle did not realize. So obviously we know that motion does not require force, only change of motion does. Okay. And this was actually realized by Galileo Galilei, who was the famous Italian, we all know of his name, who lived in the late 16th century to early 17th century. And he was, of course, famous for the heliocentric model of the solar system, which he developed from the ideas of Copernicus before him. And but here, what we are talking of are Galileo's experiments with motion, or his thoughts regarding motion, and how Galileo broke this Aristotelian ideas. So we are all familiar with this experiment, perhaps, that Galileo performed from the famous Leaning Tower of Pisa. He threw two cannonballs.
Sorry to interrupt.
Yes.
Sir.
Yes.
Sir, I am Subhasis. I like to tell Mr. Manik, sir's presentation is not here. Someone RJ Polas has been presented him. So that's why I think sir's presentation is not in the screen.
Oh, sorry. Should I
kindly see the button?
So Anwesh, why don't you just present again?
Okay. Okay, I'll do that. So, since when did you miss it? And may I request others not to present?
A while ago. The Aristotle was on the screen. So
okay.
Just
the previous slide, perhaps.
Yeah, I guess.
Okay. Okay, let me now try to go back. So was this there? Okay. So yeah, so I was talking of Galileo, who did this famous experiment of this. He took two cannonballs of different mass, and the Aristotelian idea was that the heavier mass would travel faster to the ground and would reach the ground faster, would take a shorter time. But Galileo showed that they both take the same time; they both reach the ground at the same time. So bodies fall under gravity with the same acceleration. This is what Galileo was able to prove. He went further in dismantling the Aristotelian theory. So first of all, it is common experience that no force is necessary to keep a body at rest, right? This, for our daily life experience, people understood this. But what about bodies in motion, where Aristotle said, can we have a microphone muted for everybody else? There's some background noise. Thank you. So Galileo did some very innovative experiments or thought experiments with inclined planes. So this is all there in textbooks, but I'm just repeating it just to set the context. So he realized that a ball rolling down an inclined plane accelerates. If you throw a ball up an inclined plane, it decelerates. So he conjectured that the flat plane would have neither acceleration nor deceleration because it's the midway between the two inclined planes. Okay, so that would correspond to uniform motion. Okay. Then he also worked further on inclined planes. This was more a thought experiment, but this can also be done in the lab, of course. Is that if you have inclined planes of the same incline, you slide a ball down one plane, it would rise to the same height, nearly the same height, of course. It would never quite reach the same height on the other side because of friction. We all know that. But in thought experiment, if you reduce the friction to minimum up to 0, it will reach the same height. Now, if you make the second plane at a more slanting slope, at a lesser slope, then also it will rise to the same height. But in the process, it has traveled longer distance and for longer time. Right? Now, Galileo's thought experiment was that what happens if this slant is finally made completely flat? Okay, if I just make the second inclined plane completely flat, then this ball will keep going and going and going because it will never finish its motion to rise up to the same height. Okay, so he had this idea that unless force is applied, a body in motion continues to move with uniform velocity. Unlike the Aristotelian idea, where to keep applying a force to keep the body in motion. And this property to the resistance of change in motion is called inertia. And a force is necessary to change the state of motion to overcome inertia. Okay. Now, these are all bits and pieces of ideas that Galileo had. Okay. He did not write the first law of motion, certainly not. That Newton did later. But these ideas were already there with Galileo. Further, what he realized was that a state of rest and a state of uniform motion are dynamically equivalent. How did he get to this? Because he said that, look, I mean, for example, if I'm sailing on a ship that is moving absolutely at constant velocity on a very calm motion, then if I'm on the deck, then of course I can realize that I'm moving because I can see that other boats or something are passing by. I'm passing them, or I'm passing in some lighthouse maybe. But if I'm inside the ship where I cannot look outside, I would not realize whether the ship is standing or whether the ship is moving. And all experiments that I do, and he really did do such experiments, would provide the exactly same results when the ship is moving at constant speed or when it is standing at rest. Okay? So these two are dynamically equivalent. And this, of course, on further development leads to Galilean relativity, which says that all frames of motion, all inertial frames are equivalent. But let's not get into that now. Okay, so this was what Newton had to work on. And of course, he formulated all this in the form of 3 laws as we know it, and which were first published in the Principia, as I already said. This is the famous page where he starts discussing these laws. So the first law of motion, we all know it. An object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. Now, there are several words in this formulation that we, of course, read and we understand, but I'd like to discuss it a bit further. What do we mean by an object? What is meant by at rest or at uniform motion? And what is meant by an external force? Okay. Now, our simple idea of an object is that, let's say, I have this black ball-like thing sitting on a table. Okay, it's at rest, nothing is happening. I can say that, okay, first law is valid. There's no force on it because the only force are the gravitational force downwards and the normal force of the table upwards, and they're equal and opposite. So there's no net force on this object, and therefore it is at rest. So first law is valid. But maybe, I don't know, this is not just a normal ball, there's a bomb, and after some time it just explodes. And there's obviously some motion. So one would say that, come on, how did this happen? Did first law get violated? Obviously, I mean, we don't think of such things. So what we mean by an object is that it has no internal structure or forces like a bomb has, right? So, but everything has some structure, right? Every object that we see around us has some structure. So Newton's law is actually only valid for particles. So except particles which have point masses and which have no 0 dimensions, okay? So all of Newton's laws hold strictly for particles. We sometimes use the words bodies, we use the word objects, but one has to be careful enough and understand that Newton's laws are strictly valid for particles. Of course, we know that extended bodies also follow Newton's laws, right? We see that every day in experiments, in our daily life, in the laboratory, etc. So, but this extension to extended bodies can be made using the laws themselves. Okay, I shall come to that in a minute. But Newton's laws, as they are stated, are strictly valid for particles. Now, what is an external force? Now, for particles, because they have no dimension, so every force is external, right? For extended bodies or systems, we mean forces that are not exerted by the constituents on each other. Okay, that's what we mean by external forces. All right. What is meant by rest or in motion? So, of course, all measurements of distance depend on the observer or the reference frame, correct? So, an object that is at rest in one frame may be in motion in another frame. This is all known. Motion that is uniform in one frame may not be uniform in another. So, the question is, does the first law hold in all reference frames? Of course, perhaps we can test it. So, this is again lifted from the NCERT textbook. So, you consider the case where there is a box sitting on a platform of a railway station, and there's an observer who is standing next to it on a platform. So to this observer, of course, the box is at rest. Now the only forces on it are gravity and the reaction or the normal force of the platform, and they're equal and opposite, and therefore there's no net force and the box is at rest. So obviously, he sees the box at rest and the first law holds. What about an observer on a train that is moving with constant velocity, which is just passing by? So this observer now sees this box, but to this observer, this box moves in the opposite direction with constant velocity. So for this observer also, the first law holds. What about a train which is moving with constant acceleration? Okay. Now this observer will see this box moving with constant acceleration in the opposite direction, right? Now therefore, for this observer, there is no net force on the box, right? That conclusion is the same, but he still sees acceleration. So the first law does not hold. So clearly, this third frame is not a frame in which first law holds, right? This is what we call a non-inertial frame. So a first law holds only in certain frames and not in others. So a frame in which the first law or the law of inertia holds is called an inertial frame of reference. Now, what is so much of a big deal about it? I'll come to that and you'll see why this has to be kept in mind. So now, different inertial frames are completely equivalent. There is no absolute or privileged frame, right? Now, this is the so-called Galilean relativity, or we call it sometimes the Newtonian relativity, although I must say here that Newton did have an idea of an absolute frame, because he did say that that acceleration is absolute. And of course, he was wrong, as we know from experiments done later. But now, as we know today, is that there is no absolute or privileged frame. All inertial frames are completely equivalent. And the first law is, as Newton's laws are defined, is the only test of an inertial frame. So if the first law is valid, you call it an inertial frame. Now, it goes a little further than that. Being a law, it also guarantees that it not only just defines an inertial frame, but it also guarantees that inertial frames exist. Okay. Now, a perfect inertial frame is actually an idealization, okay, because we always have some forces and therefore some acceleration. But as a very close approximation, we can take the frame of distant stars, which can be said to constitute an inertial frame of reference. Okay, all this you can find in books. So I'm just sort of reviewing this to bring forth certain subtle issues. Okay. Now, okay, so far so good for the first law. What about the second law? The second law, of course, we all know the rate of change of momentum of a body is directly proportional to the net force acting on it and takes place in the direction of the net force. This is how we write it: dp dt proportional to f, or f equal to k dp dt, where p equal to pv is the momentum. We take that proportionality constant to be 1 by suitable choice of units, and we write f equal to dp dt. Right. For a particle, because the mass does not change for a particle, so we write f equal to m dv dt equal to ma. This is the usual form that we normally know, f equal to ma. This, of course, is works very well with our normal experience. A greater force is necessary to accelerate a larger mass by the same amount. For a given mass, greater force is necessary to stop a faster object. Okay, this also we know from common experience. I'm trying to skip a little bit because there's not a lot of time left. So it seems that the product mass times the speed, that is the momentum, is related to the force. Okay, so this is the idea that Newton also had. Okay, he realized that this quantity called the momentum is of relevance. Okay, because we see that that larger mass requires larger force, and larger speed to change it also requires to make larger change in speed also will require greater force. Therefore, this product is something that is useful. Okay. So changing the momentum by a given amount in a shorter time requires more force. This also we know from common experience. If we, for example, if you're trying to catch a ball, if we try to bring it to rest very quickly, we require a larger force. The ball hurts our hand more. But if we pull the ball in our hands a little bit so that we elongate the time during which this change of velocity occurs, then we require a less force. Same force acting for the same time causes the same change in momentum in different bodies. Okay, this we can do all this by experiment. Change of momentum happens in the direction of the force. This also we know. So overall, the rate of change of momentum is proportional to the force. Okay. Now, I only talked of the change of the magnitude of momentum, but momentum can also change in direction only and not in magnitude. For example, in uniform circular motion, and this also requires force, as we just saw the centripetal acceleration. Okay. So why are we talking of all this? The question is that the second law defines force. Okay. So there's no independent definition of force to verify second law. Okay. Can we not have an alternative definition of force? Perhaps yes, but it will not be very useful. Only the definition as given by second law determines the motion of the body, because you can predict the acceleration and therefore the motion of the body from that. Okay. For most forces in nature, we have an explicit form of the force F. Now, notice that F equal to ma does not solve the problem for you. Okay, now this is a common misconception that perhaps sometimes students have. They think that F equal to ma will immediately solve the problem. No, it will not, because you still have to specify what is that force. You have to say whether it's a gravitational force, whether it's an electromagnetic force, whether it's tension or something like that, whether it's friction. So you have to define the F. You have to specify the F, and only then you can predict the motion. even that is not enough, right? Just knowing the second law in the form of the force is not enough to solve the problem. Why, you may ask? Because this is a differential equation and it needs initial conditions to determine the motion. As an example, for example, if you throw a stone vertically upwards and you throw another stone as a projectile, as an angle, Newton's second law is the same, F equal to ma in both cases, right? I'm talking about the vector law. F vector equal to ma vector. That's the same. Even the specification of the force is same. In both cases, is gravitational force. If I neglect, for example, the air resistance or something. Yet, you know that the motion is very different. One just goes straight up and comes straight down. The other one describes a parabola, right? Why is this? Because the initial velocity is different. The direction of the initial. So the initial conditions are what actually determines the solution. That's what makes all the difference. Okay? So you need Newton's law, you need the specification of the form of the force, and you also need initial conditions. So only then you will be able to solve the dynamical problem. All right? Okay. Does the second law hold in all kinds of frames? No, you all know that. It can, so for example, in our previous example, in the platform frame and in the train moving with uniform speed, of course, they both say zero acceleration, therefore zero net external force, so second law holds. But in the third case, there is non-zero acceleration. Okay, so one would think that the net external force is acting, so the second law does not appear to hold. We can make the second law hold by inventing something called the pseudo force in a non-inertial frame or an accelerating frame. This also you will learn from textbooks, you all know it, so I'll not go into that now. Okay. So sometimes what happens is that we don't realize that why these different laws are there and what is their importance. Okay. So in many cases, sometimes we appear to prove the first law from the second law. This seems to go like this, that okay, F equal to ma, I'm talking of the one-dimensional case here. Now if F equal to 0, then A equal to 0, since m for a particle cannot be 0, right? So then if F equal to 0, A is equal to 0. There is no force, no acceleration. Isn't that exactly what the first law says? So I can say that the first law is a special case of the second law, right? I may be tempted to say this, but you should realize that this is wrong. This is not the correct interpretation. Why? Because the second law is valid only in inertial frames, and the first law defines what is an inertial frame. Okay. Once you have defined the inertial frame by the first law, only then you can apply the second law. Then it is a circular argument, right? So the validity of the second law presupposes the validity of the first law. So then there's no point in saying that, okay, if F equal to 0, then A equal to 0. It is not superfluous unless you have determined the frame to be inertial by checking whether the first law holds. You cannot even apply the second law, right? So that's why the first law is not redundant. Newton, who is considered one of the greatest minds ever, was not so careless as to give two laws, one of which can be subsumed in the other. No, he realized that he needed these two laws separately. Okay. Similarly, for the third law of motion, which we'll see later. So the third law, the usual description is like this. To every action, there is always an equal and opposite reaction. Okay. Now, this was actually Newton's formulation. This is quite crisp and concise, but it gives rise to many misconceptions. Okay. First of all, one has to realize that both action and reaction both of them are forces on equal footing. They're completely equivalent. There is no precedence of action over reaction, because in normal parlance, the words action and reaction happens that way, right? There is some action, you hit your friend hits you back, right? That's a reaction. The prime minister says something, the leader of the opposition says something in response. Action and reaction. But in physics, it's not so. Action and reaction are both forces that are simultaneous. Action does not precede reaction. They arise at the same moment. They act on different bodies. This is another thing to keep in mind. They can never cancel each other. Okay, and they always appear in pairs. So a better formulation of third law perhaps would be that like this: forces always occur in pairs. The force on a body A exerted by another body B is equal and opposite to the simultaneous force on B exerted by A. That covers all bases. Okay. If you just say action to every action there is an equal and opposite reaction. Sometimes we are misled. So don't be misled. Okay? We know that the principle of conservation of linear momentum can be derived from Newton's laws of mechanics. This is worked out always in textbooks. However, one should also realize that the principle of conservation of linear momentum goes much beyond mechanics, even in situations where the third law is not valid, for example, for forces between charged particles in motion. Okay, this is just a remark. Now, how do we go from particles to bodies? So this is how. So for a system of interacting particles, the total force on the system is the vector sum of all forces exerted by the particles on each other and all forces exerted on the particles by external agencies. Okay. You have to take the vector sum for a system of interacting particles. The first sum becomes zero due to the third law. Why? Because when you sum over all the forces that the particles apply on each other, there will be pairs that will cancel out. Okay. You have to understand clearly that the forces on individual particles is not zero, okay, from their neighboring particles. Okay. But the sum of all internal forces on all particles is zero by the third law. Once that is done, then the net motion of the system is governed only by the net external force. So here is how we transition from particles to a body. That is why Newton's second law works for extended bodies. You need the third law to affect this. Okay. So Newton's second law says that the rate of change of momentum of a particle is proportional to the force applied on it. Okay. It does not say that the rate of change of momentum of a system is equal to the net external force on the system. That is a result that is derived from the second and third laws. Okay, you need the third law. So the third law is not contained in the second law. Sometimes you will see proof of how the third law can be proved from the second law. Okay, that is completely wrong. That is bogus. You should be careful. It cannot be proved. Okay, many sources erroneously claim this. You will find on the internet many places where people have done this kind of thing. Even in some textbooks, this is sometimes given. Please understand that this is wrong. Okay? Wrong and bad physics. So please be careful about your source of information. Okay, I think I will stop here with that advice. I have to thank several sources and several people. So the references are this book I already mentioned, Never at Rest, which is an excellent biography of Isaac Newton by Richard Westphal. Then there's this wonderful book on by Simmons, which also has a good historical account of this whole story. Carl Sagan has described it very nicely in his book and his series called Cosmos. The NCERT book also gives actually some account of this. And there are two wonderful books, one by A.K. Raichaudhuri on classical mechanics. This is not easily available. The other one is very easily available, Klepner and Kolenko, Introduction to Mechanics. And to all, at least undergraduate students, I strongly recommend this book. I have been much helped by discussion with some colleagues, Professor Arvind Kumar and Professor Ananda Dasgupta, especially Professor Arvind Kumar in detail. So I will let this be in front of you when I finish. So these are some of the quotes by the famous man, Isaac Newton himself, who says that if I have ever made any valuable discoveries, it has been due more to patient attention than to any other talent. Of course, this is a very modest statement. But what I want to emphasize is that science requires not only flashes of brilliance, not only talent, but a lot of hard work, a lot of careful attention, as Newton says. He says, to myself, I'm only a child playing on the beach while vast oceans of truth lie undiscovered before me. And finally, the statement from which I've taken the title of this talk, if I have seen further, it is by standing on the shoulders of giants. And no doubt, he was a giant himself. Thank you. Thank you for your attention. Sure. Yeah, I'll be happy to answer. Yeah.
Hello, sir.
Yes.
Good evening.
Good evening.
Sir, my question, I have two questions. One question is related to the Kepler's first law. Sir, what was so special in the observational data of Tycho Brahe which proved that the motion of the planet is elliptical?
I don't know what you mean by so special. So, I mean, if you, so in the sky, of course, I mean, see the planets move very slowly, right? They're not, I mean, describing arcs of ellipses every day, correct? So you have to observe the planets very carefully. And over time, you also need to use three-dimensional celestial geometry to understand that the planets are actually describing elliptical paths, that they're distance from the sun, and you are not on the sun, right? You are also on another planet. So it's not easy. So the distance from the sun goes as it would be for a particle or a point moving around in an ellipse with the sun at its foci. So that was special. I mean, how do you determine it? I mean, if I tell you that it's a circle or it's a parabola, I mean, what's wrong in that? Of course, the data does not support that. The data shows that it is an ellipse. That is what, and for that it requires extremely precise and many observations, which Tycho Brahe did very painstakingly. Okay. Does that answer your question? What is the second
yes,
question?
Sir. Yes, I got it, sir. The second question is, sir, you mentioned that using Newton's third law, Newton's proved that the gravity is proportional to the product of masses. Like you said.
No, he did not really prove it using third law. See, the point is this following. So he had figured out that the force with the relationship with the distance is inverse square, right? Now he saw that. I mean, Galileo had already proved it with his cannonballs experiment, right? That the acceleration does not depend on the mass, right? This was already known. It was shown by Galileo. And he correctly surmised that it must be so for the moon and the planets also, right? So the acceleration is therefore not dependent on the mass. The acceleration is inversely proportional, but our common experience shows that the force is proportional to the mass, right? So then one would think that then the force can be a product of the mass and the acceleration. So that is proportional both to the mass and the acceleration. Now that is a force, let's say, that the Earth pulls the apple with. Now Newton's third law shows that the apple says that the apple pulls the Earth with the same force, right? Now, if the force contains only the mass of the apple, then that would be very hard to now justify, right? So therefore, it must also contain the mass of the Earth, right? So that it is not just m1 by r square; it has to be m1 m2 by r square. That's how he obtained it. Does that explain the answer?
Sir,
it has to be reciprocal.
Why not any other operation like addition?
That would not satisfy. No, you try it. I mean, what kind of operation? You cannot have things proportional to both A and B. So A plus B is not proportional to A and B. AB is, right? If you keep one. Yes.
Thank you, sir.
Okay. Yes, please ask the question. How to become an astrophysicist? Okay, there is no formula for this. If you are a student, I suppose you are a student. So what you need to do is to learn your physics and mathematics very well. Okay, till all the way up to your masters. Okay, you don't need to really study astrophysics. Specifically, of course, if you have an interest, you should, and you are most welcome to. But it is not necessary that you should learn a lot of astrophysics or astronomy before you finish your masters. But you must have your mathematics and physics very strong, because those are the basis of astrophysics. Okay, astrophysics is based on physics and mathematics. So that's what you need to do. And then after masters, you can certainly choose astrophysics as your PhD topic. And during PhD, you have enough time to learn the topic well and do your PhD. And from there, you start doing research in astrophysics. That's how I suppose you become an astrophysicist. Of course, later in your life also you can become an astrophysicist. You may start doing research in something else, maybe high energy physics, let's say, or condensed matter physics, and later on you can switch to astrophysics. That's up to you. So it's but you need to have a firm grounding in physics and mathematics. As a student, that would be my only advice. And certainly, if you're interested in astronomy, you should read good books on astronomy, on introductory astronomy. Yeah. Yes, so this is exactly what I told you when so that was the whole point. All the three motions are fundamental, all are necessary. There is no preference over one. This is the whole point that I want to impress upon. That, see, this proves that Newton's second law is a real law of motion. This is bogus. Okay, as I showed, that the second law is valid only for inertial frames, and for inertial frames, you need the first law to define it. And the third law also cannot be proved from the second law. Okay, you can use the third law and the second law to extend from particles to extended bodies. So there is no point in this question that which is most fundamental. In any case, I think in physics, there is no point in asking whether one law is more fundamental than the other. Okay, what purpose does it serve? If I tell you that the second law of thermodynamics is more fundamental than the first law of thermodynamics, how does that help in anything, right? You still need the first law of thermodynamics, correct? So please don't bother about all these, which is more fundamental, which is more basic, etc. You should understand the physics behind it, and you should also understand that if it, I mean, the whole idea of science and physics is to obtain the minimum set of laws in any case, right? If you had a law for every object, for every phenomena, then that would not be a very good science, right? So scientists and physicists try to unify things, right? So that various different kinds of phenomena can be obtained with a minimal set of laws of nature, like Newton did for the apple and the moon, right? So, and then there are the fundamental laws. Yes. No. I don't know of any place on Earth or anywhere in the universe where there is repulsive gravity. That has not been discovered yet. There is, of course, in the universe, there is, in the accelerating universe, we think that there might be something called dark energy, which acts something like negative gravity, but that is, its relation to gravity is also not understood. Nobody understands what really is the dark energy. So let's not talk about that. Yeah.
Good evening, Professor.
Yeah.
I had a question, if I can go ahead.
Yes, please.
Yeah. So, how about the forceless mechanics, which is just based on acceleration? Would it work? Would it be good? How about the forceless mechanics, which is based only on acceleration, which does not has the idea of force? Because in some sense, force looks up like a very made-up quantity. You take mass, you take acceleration, you multiply that. Yeah.
Forceless mechanics.
So, yeah, in the sense that it does not have the idea of a force. It uses only the idea of an acceleration. So, like if we have a law for right now, we have a law of gravitation.
That is kinematics. So that is called kinematics. So basically, you can. So the point is that, see, you have to understand that you said that the force is a made-up thing, right? So why do we make up things? Because we want to explain. We want to understand what makes the Earth go around the sun in an elliptical orbit, right? You cannot ask that question. It is your choice, of course. You may be least bothered about that question anyway. Just say, okay, let me see how the Earth goes around the sun. It's fine. It goes in an ellipse, and you rest there. But usually the human mind is not so easily satisfied. They want to know the why of it, not just what and how, right? So that's the whole idea. So what you are saying is what is called kinematics, where you only describe the motion. You do not wonder about why is it happening, and thereby you also lose the power to predict its motion in the future. It has no predictive power. If you don't know why it is happening, you don't know something, whether that is moving in a straight line now, whether it will move in that same line in the next second, right? If you don't know whether there is a force or not.
So how about we go on doing it like this, instead of saying that, okay, force is this and it has this expression GMM upon. What?
No.
Yes,
I'm trying to understand what is your motivation. What do you
Yes,
mean
so the
going on
motivation-
doing about? Yes.
Yes, so the idea is that we say that okay, the acceleration is given by gm upon r square.
How do you know
So,
that? How do you know that? If you don't know the force, how do you know that the acceleration is given by gm by r square?
Right. So if I have any given body, then I can look at it how it is moving.
This is an exercise that you can do if you want to just describe the motion. Of course, you can do that, but you will have no predictive power. So I don't understand even what you mean by if we go on doing that. You cannot go anywhere unless
Okay.
you know what is causing the motion. You lose the predictive power, as I already said, right? If you don't know, I mean, the acceleration is determined by the force. If you don't know the force, you don't know what. So you're talking of the instantaneous acceleration. What about the acceleration in the next instant? How do you know whether it's going to be the same or whether it's going to change or whatever, right?
Right.
Unless you know the force.
Yes.
So you cannot go on doing anything like that, right? Yeah.
Okay.
Okay. Yes. Any other
Can
questions?
I come in here?
Yeah, please.
Can I comment on the last question?
Yes. Who is this? Sorry.
My point is that one way of going beyond the forceless thing would be to simply say that ultimately what Newton's second law really tells you is that particle's acceleration is dictated by its position and velocity and no further properties are needed. And of course, position and velocity of all the particles. That rule
Ananda, your voice is breaking. Your voice is breaking.
Breaking. Sorry, I'm using a different system, so I'm not really sure whether it's carrying properly.
It's much better.
What I wanted to say, okay, now I'm closer to the mic, I guess. All I wanted to say is you can always say something like, like say second law, you don't really need a force. You can just say that the acceleration is dictated by a rule which you can calculate given the position and velocity of the particle. But that rule is exactly what you call the force ultimately. So whether you want to call it a force, whether you want to use the name force or not is unimportant. What second law is telling you is that if you know the position and the velocity of a particle, then there should be a rule which tells you how to calculate its acceleration. Now, whether you want to call that rule due to a force or not is up to you.
Right.
But
I would also, yeah, thank you, Ananda. I think I would also like to emphasize that, I mean, it is important to point out that these names of different quantities and calling something this or that actually does not have much meaning, right? I mean, it is only for communication among ourselves, right? If you, I mean, that would not change the way nature works. Okay, whether you call something force or something energy, it is up to you, as long as that convention is obtained by anybody else. So as Ananda said, I mean, you may call the mass times acceleration by, or you may not give it a name. That does not change at all the way nature works. So, so that is inconsequential. It is only for our convenience, of course, that we label some of the useful quantities as something, right? Okay. Yeah. Any other question?
Okay, sir. Thank you.
Thank you. Thank you, Manik. It has been a pleasure, and certainly yes, these are difficult times, especially in the middle of the pandemic, and it is good to have some academic discourse going on. And I appreciate the efforts that you have taken to keep this going on through your organization to organize these webinars. That's very praiseworthy, and thank you for that. And thank you once more for inviting us. It has been a pleasure. Thank you. Okay.
Yeah.
Hello?
Yeah, seems like yes. Okay. Thank you. Can I leave now? Thank you. Thank you.
Would this video be available on YouTube on your channel? Okay, thank you.
মানিকবাবু ফিডব্যাক ফর্ম মেলে দিয়েছেন? হ্যালো মানিকবাবু, ফিডব্যাক আচ্ছা।
এখনো চলছে দি?
না,